So in this video we will start to see how to construct confidence intervals and how to interpret them. So we will start with confidence intervals for discrete variables. So in this video in particular we will see for proportions. So let's start. So our goal, as we said in statistics, is to go from the sample to the population. But to do that, we need first to understand how from the population we go to the sample. And that, if you want, you can think of it as a simulation. So there are three statistical distributions that are discrete distributions that are of use in this context. Those ones are the binomial distribution, the cumulative binomial, and the negative binomial. And each one has a different, slightly different setup. So the binomial is probably the most well-known one. And then, for instance, let's say that we flip a coin that is fair, so the probability of having heads is 0.5, and we flip it 10 times. So the 0.5 will be called P, the 10 times will be called N, and we wonder what is the chance of observing exactly 7 heads. There is a formula to calculate that. So the binomial distribution is the probability of observing exactly R independent successes. Successes is the event that you are interested in out of N when each one of the successes has a probability P. And for instance, if instead of coins we have a different setup, for instance, what is if the probability of getting an infection after a surgical operation is 5%, what is the chance that exactly 10 in the next 30 patients will get an infection? And we can calculate that probability through some particular formula. The cumulative binomial distribution is slightly different. It is what is the chance that 10 or more, and this is the difference, 10 or more, before it was just exactly 10, so 10 or more of the next 30 patients will get an infection. So it is the probability of observing R or more independent successes out of N when each one of the successes has a probability P. And the negative binomial distribution is again a slight variation with respect to the previous ones. So what is the chance of observing 30 non-infected patients before we observe the first infection? So it is the probability of observing Q independent successes before observing R failures when each one of the failures has a probability P. And there is an advantage of this negative binomial distribution, that is that there are a couple of parameters that you can feed to your data. So it is very much used, not so much because it explains the way the data is generated, but simply because it fits the observed data. So we have in the previous slide we have gone from the population to the sample. So if the probability of success is 0.5 and I take a sample of N equal 10 coins or 10 patients or 30 patients, what is the probability that I expect in that sample? Now we will go the other way around. We go from the sample and we try to infer what is the P in the population. So for instance, let's say that for premature babies born at Johns Hopkins Hospital between 1993, we have observed that from 29 babies that were born at week 22, none of them, so 0 of them, survived after 6 months. But if they are born, instead of week 22, they are born on week 25, then out of these 39 babies that were born on week 25, 31 of them survived after 6 months. So the survival rate here was 0/29, that is 0%. The survival rate here is 31 divided 39, that is almost 80. So the probability of surviving if you are born on week 25, the observed value is 79.5, and the observed value and the probability of surviving 6 months if you are born on week 22, it is 0. So are the true probabilities of survival exactly 0 and 79.5? Probably not. So probably if you repeat this experiment in some other hospital, and assuming that the two hospitals are the same, the numbers that you will get will be close to this 0 and 79.5, but they will not be exactly those. So can we give a confidence interval that contains the true proportion with probability 95%? The answer is yes. So again, there are formulas. We will see them at the end of this video. And if you apply these formulas to this data that you have observed, the confidence interval of 95% confidence is from 0 to 14. So we have observed 0, but it is reasonable that the true parameter of the population is between 0 and 14. And for this 80%, it is between 64 and 89. And there is a remark to do here, that is, these confidence intervals do not need to be symmetric. So for instance, this is almost 80, and this goes from 64, that is 16 units away, to 89, that is only 9 units away. So it is wider on the left than on the right. So confidence intervals are only symmetric for those distributions that are originally symmetric, and the one of the binomial distribution is not. So for when things that are when the variables that are involved are symmetric, like Gaussians or things like that, then the confidence intervals are normally symmetric. And then these intervals only account for the sampling error. So this uncertainty that we are calculating here is only accounting for the sampling error of the sample. So because you have not observed infinitely many babies, just 29 or 39, you have an uncertainty associated to it. So if instead of observing this amount of babies you observe more, your confidence interval will be reduced. So there is less chances that you are really missing some effect. So what we are observing is closer to reality. So they account only for sampling error. They don't account for bias. If you have a biased experiment, these confidence intervals are completely wrong. It depends on how much bias you have. But if you have a lot of bias, these confidence intervals will be completely wrong. So what are the assumptions when we are computing these confidence intervals? What are the assumptions we are doing? So and this is the main assumption that is done in statistics in many places. It is assumed that the sample is random. That means that it is representative of the true population. So other than chance, there is no systematic difference between the newborns at Johns Hopkins Hospital and the general populations. So we are assuming that there is no difference in nutrition of the mothers before giving birth. There is no difference in the medical care to the newborns. There is no difference in the hygienic state of the hospital. And then, if this is true, then we can generalize this 80% of survival to the whole population of newborns at week 25. Otherwise, we can only generalize it to the newborns with conditions that are similar to the ones of that are born at Johns Hopkins. So we are also assuming, when we extrapolate to a more general population, we are also assuming that this proportion is can be used to predict, and it can be used to predict under the same conditions of location, time, medical knowledge, etc. So for instance, if you change your location, if you think of newborns at Johns Hopkins and newborns in Africa, probably they will have different conditions in terms of nutrition, medical care, hygienic state, etc. Also, they can be used to predict only if there is no change in time. For instance, if you compare this survival rate 20 years later, probably the medical knowledge, the medical care, and all the treatments that are done on the newborns that are so small probably is different. And then this proportion of survival does not apply anymore. So when you generalize from one sample to the population, you're assuming that the sample is representative and that this proportion, this parameter, stays fixed over conditions, over location, over time, etc. We are also assuming that we have independent observations. So if two twins survive or two twins die, they are not independent. They share all the genetic background. They also share the environmental factors. Or, for instance, if deaths are correlated because there is a hospital infection that affect some of the newborns, then these proportions are not independent anymore, and these confidence intervals that we are calculating, they are not correctly calculated. So there are corrections for correlated data, but the formulas that we use normally, they are not corrected for correlated data. And it is also assuming, when we construct the confidence interval, we are also assuming that the data is accurate. So for instance, if the doctors know that 6-month survival is to be tracked, they may make heroic efforts to bring a 5-month-old baby a few days more so that he accounts. And even if he dies a few days later after these 6 months. So there is no bias. This practice would be biasing the proportion of survival. So and there are many other, you can think of many other ways of, it is not cheating, it is something human, but many other ways of biasing and making the data not to be accurate. So what is the confidence interval? So the true population proportion lies or lies not in the 95% confidence interval. There is no way to know if it does or if it doesn't. So the true proportion of survival for this type of babies, it is somewhere here or it is not, but the true proportion one. But we don't know in which case we are. So let's see what the confidence interval means. It means that if we repeat the experiment, and the experiment is taking a sample, computing the average proportion, and then calculating the confidence interval many times, in 95% of the occasions, our confidence interval will contain the true population proportion. Although we don't know which ones to contain it and which ones don't contain it. So 95% is the probability that our confidence interval contains the true proportion, even if we don't know if in this particular example it does or it doesn't. If the true parameter is outside our confidence interval, it is due to bad luck with our samples. This is called the sampling error, and this occurs in 5% of the cases. 5%, that is the complement of this 95%. So actually there is nothing special about the 95% except tradition. So if you want to be more sure about your statement, so only in 1% of the cases you commit an error, and the true proportion parameter is not in your confidence interval, you will have to make your confidence interval larger. Or the opposite. If you want a narrower confidence interval, then you will have to lose confidence in your results. So if I think that this confidence interval is too wide, 26% of distance between the lower limit and the upper limit, so that is too much. I want a narrower confidence interval. Then you can construct it narrower, but then instead of this confidence interval containing the true parameter with probability 95, it will contain the true parameter with a lower probability, 90, 80, or whatever. Actually, the confidence, this 95% confidence, is on our procedure to construct the intervals. It is not about this particular interval. So what we are confident is that if we repeat this process of constructing confidence intervals many times, in 95% of the cases, we will contain the true parameter. So 95% is not the probability that the true proportion is in our confidence interval. 95% confidence interval does not mean that 95% of the sample data falls within this interval. 95% confidence interval does not mean that with probability 95%, if we repeat the experiment, the estimated proportion falls within this interval. So actually the first one, I think it is wrong. So it does mean that the confidence interval contains the true proportion with probability 95. Okay, so I mentioned the formula, the formulas to construct these confidence intervals, and you see that we have everything. So R is the number of successes, so these 31 newborns that survived. N is the number of newborns that we have observed, and alpha is the error with which so this 5% error that we allow to. So when you want to construct a 95% confidence interval, this alpha is 5%. So you have everything. So F is a distribution, so that this is a number, this is the number, is a number such that for the FS curve with these degrees of freedom, there is a 1 minus alpha half probability to the left. So you have all the numbers to substitute. It looks complicated, but it is simply substituting, and the computer will know how to do this substitution. And since this is too complicated, there are simplifications, and these are some of the simplifications. So for instance, we can construct a confidence interval that is symmetric. So the true proportion is between P prime minus W and P prime plus W. And this P prime is calculated like this. So we have everything again, and for the 95% it is a very simple formula, and then W is calculated like this, so it is a function of P prime, and the rest we also know. And again, for the 95%, this set is the percentile 1 minus alpha half for the Gaussian distribution, for the standard 0-1 Gaussian. There are more approximations. So if you observe very few cases like 0, 1, or 2, there are confidence intervals that are they are left bounded at 0, so they are only constructed from 0 to some upper bound, and this is the upper bound, 3 over n, 5 over n, 7 over n, etc. There is a common mistake, that is interpreting any percentage as a proportion. So for instance, let's say that we give an antipyretic to mice, and the temperature drops from 39.5 to 37. So that is a temperature drop of 6.3%. But this 6.3% is not a probability. It is not the probability of the occurrence of any event. It is simply a continuous change, or it is a change in a continuous variable. So this variable, the temperature, that can take any value in between. The mean has gone from 39.5 to 37, and this change is 6%. But it is not any probability of the occurrence in the same way as the probability of getting herpes or getting an infection or surviving after 6 months and so on. So not for everything that can be expressed as a percentage we have to construct a confidence interval using this kind of formulas. This is only valid, and actually this is only valid for the binomial distribution. So this is it for today, and tomorrow we will see survival data.